So what we're going to be doing in this unit is you have to be able to identify whether a function is polynomial or not. That's a classification. There are these definitions of things. One is going to be the definition of degree, the definition of multiplicity, the definition of symmetry. And we're going to have to be able to describe the graphs of polynomial functions by looking at the degree and the multiplicity and the symmetry. There are two very important layers in this mathematical sandwich called the remainder theorem and the factor theorem that we're going to be spending a lot of time on. And then we start pulling everything together in order to graph polynomial functions in detail. One of the other things we're going to do is look at transformations of polynomial functions, but I'm not really too concerned about that. The diagram at the top, or the graphic at the top of your title page of this handout, we'll get to, because you will learn why. Well, I hope we would all agree that the picture on the left is odd. There was a time in the late 70s where that was normal and admirable to dress like that and dance like that, which is very odd looking in retrospect. But we will learn in today's lesson why that polynomial function is odd as well. And the only thing I will say to you without understanding the nature of the word odd for graphs is you can see that there's a certain curve in John Travolta's stance there that matches the curve of the function. Specifically, you have his left, well, the arm on the left of the diagram is pointing towards the sky. The arm on the right is pointing towards the floor, just like the graph on the right is. All right, so we're going to get started here and plow right into it. This is on page 1 of your unit handout that I've just given you. Of all of those things that I talked about that we're going to be doing in the unit, a couple of them we're going to be doing today. And this is a relatively short lesson. We're going to be identifying a function as being polynomial. We need to talk about what the degree of a polynomial function means, what the leading coefficient means. So not just, when I say what it means, I mean you have to be able to identify the degree, and then you have to be able to tell me what it tells us about the graph. The same with what's called the leading coefficient and also the constant term. And basically, putting all of that together, you should be able to tell me something about the graph of a polynomial function in terms of numbers of x-intercepts for each function. We're not going to be at the stage today where you can graph a perfect picture of a polynomial function. But you will be able to at least tell me something about the x-intercepts, the general shape, and what's called the end behavior. So we start off with a definition of a polynomial function, which is really quite intimidating, this definition. It's highly mathematical, but let me break it down for you. This says that a polynomial function of x, which just means an equation that you can use by putting in x to calculate a y coordinate, if you want to graph it, is in general form is a sub n x to the n. So let me stop right there and tell you that n is a natural number. Okay? N is a number like 5 or 100 or 2 or 1. N can actually be 0, so I'm going to amend what I just said and say that n is a whole number. I've always remembered that whole numbers include 0 because a whole looks like a 0. Okay. What I want you to note about this first term, this would be, we could call it term 1, or the first term. And you can write this down or not. It doesn't matter. This is going to all come together and it will make sense to everybody eventually here in about 10 minutes or so. What you need to understand about this first term is that a sub n is just the coefficient. Of the first term. Okay. A sub n minus 1 would be the coefficient of the next term. All of these a's with the subscripts are just coefficients. So when you talk about n here, and I'm going to give us an example to begin with, okay? And you have limited space here, I understand that, but if you decide to write this down, that's fine. I would prefer if you just pay attention and think and listen. If I were to give you a function like f of x equals 3x squared plus 8x minus 5, then what I would be telling you is that n is 2. And I would be telling you that a sub n is the number 3. And I want to try to make a very important distinction between the n that's highlighted in yellow and the n that's part of what's highlighted in blue. The n that's the exponent is an actual mathematical operation. It means squared in my example. The n that's in the blue part that's highlighted, a sub n, I guess I can tell you that this is a sub 2, right? But all that 2 is a label. All it's saying is it's the coefficient of the term that has 2 as an exponent. That's all. It's not a mathematical operation. It's just a label. And for that reason, a little bit later, I'm going to not even write these subscripts because they're unimportant. They're not mathematical in nature. They're just labels, that's all. So a polynomial function is any function that looks like that. You'll notice the exponent on n drops by, or the exponent on x rather, drops by 1 to get to the next term where it becomes n minus 1. Then it drops by another 1 to become n minus 2. And then it keeps dropping until you get down to something times x to the 1. And if you like, something times x to the 0, because x to the 0 is 1. In other words, everybody, quadratic functions are polynomial functions. We've got x to the 2, x to the 1, x to the 0, and there are coefficients in front of the terms. Another example of a polynomial function would be f of x or y equals 2x minus 8. That's a polynomial function. It happens to be a linear polynomial function. The key idea here, everybody, is that all of these a's are coefficients. I'll talk about a not being 0 in a second. And n, which is the exponents on x, are whole numbers. So why can the leading coefficient, the coefficient of the first term, why can it not be 0? Does anybody know? I know this is still at the abstract stage, but why would we not want the first coefficient to be equal to 0? Marcel? Right, because 0 times anything is 0, which means if the first coefficient was 0, that wouldn't be the first term, would it? It would be the next term that would be the first term. So it's just a mathematical definition that the first term cannot be 0, which would happen if the leading coefficient is 0, because if the first term is 0, then it's not the first term. Okay, so don't get bogged down with that. So, which of the following are not polynomial functions? Remember what we've said. Well, let me back up. These are coefficients, and they have to be real numbers. I hate the fact that in math in high school, we have to talk to students about real numbers when we never study non-real numbers. Okay? All the numbers we learn in high school math are real numbers. Does anybody know what a non-real number is? Have you ever heard of an imaginary number? An imaginary number is a non-real number. Now, I hate the word imaginary because it seems to imply that it's this thing that we just think about. An imaginary number is a number in the number system that is actually used in certain branches of science, and it's used in branches of science to come up with solutions to problems. Okay? The solutions work. Non-real numbers are things like square roots of negative numbers. Okay? Any other number is real. Ian, go ahead.
I was actually going to say root
root negative 1. And that's the classic example. That's a non-real number or an imaginary number. Thank you. So which of these are polynomial functions? Well, which are not polynomial functions? Well, this one's not. Can somebody explain to me why this is not a polynomial function? Jonathan. Right. And a third is not a whole number. Those exponents have to be whole numbers. So the problem here with this, well, it's not a problem, but in terms of calling it a polynomial function, that's a problem because you cannot have a fractional exponent. It must be a whole number. This one is not a polynomial function. Can somebody explain why that is not a polynomial function? Wayman, do you know? Right, it has a non-real number as a coefficient. So the problem here is the coefficient of the square root of negative 3. You cannot take this. Well, in high school math, you cannot take the square root of a negative, so we call that a non-real number. This is not a polynomial function. For the same reason that a is not a polynomial function, and that reason being is that the exponent on one of the variables is not a whole number. It happens to be a negative. This is a difficult one to explain. So I'm asking you to kind of stick your neck out if you think you know. Why f of x equals x minus 2 over x plus 3 is not polynomial. Jonathan.
Because when you first start, a polynomial function is any function of form a n x n plus.
Right.
Function f isn't a function because it's division.
Oh, that's a good way to put it. This is division. Nowhere in our definition of a polynomial function do we have anything that says we're dividing by x's. And I like your answer better than what I had in mind. What I had in mind is I was going to say this is not a polynomial function, e, because it just doesn't fit the pattern. A number times x raised to an exponent plus a number times x raised to an exponent. But that's a very important idea that you pointed out here, that nowhere in our definition of a polynomial function is there division by variables. This is actually a rational function, what we would call a rational function. Ian, go ahead.
In the definition, it only has division signs. Are you allowed to have a negative?
Are we allowed to subtract terms? Yes. And the reason we're allowed to subtract terms, that is covered in the definition because A0, A1, A2, all of the coefficients are any real numbers. So those numbers can be negative. So if, for example, this coefficient is a negative number, then it will be minus that term, definitely. One other thing I want to point out to you, I'll switch to y for this, is that this is a polynomial function even though it doesn't have every exponent from 4 down to 0. Polynomial functions could have, an x to the 4, an x to the 3, an x to the 2, an x to the 1, well, an x to the 2, an x to the 1, an x to the 0, and it could be that it is 0x to the 3. So you don't get x cubed. And I bring that up because you should just know that you don't need every single degree or every single exponent all the way down to 0. And I was triggered into thinking about that because those coefficients can be negative, making the terms negative, or those coefficients can be 0, making those particular terms 0. All right, and back to this. I'm going to tell you that this is not a polynomial function, but this is a polynomial function. And I'm asking everybody to think carefully about what the difference is between those two functions that would allow D to be a polynomial function, but B is not, because they're almost identical. Leslie, do you know?
I'm not sure the exact reason, but the exponent on the 3x is a 3, and I know that's not allowed. I don't remember. It was from last year.
Right. So we can put it there. It's allowed, but it's just not going to give us a whole number for an exponent on x. And the reason is there's lots of ways to explain this, but the square root of x to the 4 is x to the 2. It's half of that exponent. The square root of x to the 3 is x to the 3 halves. So if you were to apply, I'm not going to worry about the 5x plus 2. This is exactly right what Leslie said. If we take the square root to mean an exponent of a half, which is what it means, and we apply it to that x, you're going to end up getting in here root 3, and then you're going to have x to the 3 halves, but 3 halves is not a whole number. It's fractional. If we do the same thing here, this is going to become, well, I'll just leave it as root 3. It's going to become x to the 4 raised to the half. And when you multiply those exponents, because that's what you do when you have a power of a power, you're going to get 4 times a half, which is 2. So this becomes root 3 x squared. I don't think the idea of identifying a function as polynomial or not is really a big part of this unit. It's not like you're going to have a written response question on it. But I think this example at least introduces a bunch of discussion between us about possible values of coefficients, possible values of exponents for polynomials. All right. So what is the degree of a polynomial function? The degree of a polynomial function is the highest degree of all the degrees in each term. I'll remind you that the degree of a polynomial term is the exponent on the variable. So for example, if I had p of x, I'll just use p for polynomial, equals 10x to the 5 plus 4x squared plus 2x minus 8. The degree of this term is 5. The degree of this term is 2. The degree of this term is 1. And the degree of the final term is 0, because we could write x to the 0. So that's how we identify the degree. Degree is just a weird word that we use in this context to mean exponent. So if you look at the top line, the degree of the polynomial function is the highest degree of any term. That means this polynomial function is a degree 5 polynomial function. Okay? It's the highest degree. The leading coefficient is the coefficient on the term of the highest degree. So this would be degree 5. And the leading coefficient of this polynomial function would be 10. It's the coefficient of the highest degree term. It's called the leading coefficient because when you write a polynomial function, I don't know if you've noticed, but I've been writing them with degrees decreasing. So you start with the highest degree and you decrease it. The constant term in a polynomial function is the term, well, it's the term that's constant. I mean 10x to the 5, this, and this all depend on x. They're variable. But negative 8 is constant. So the constant term here in my example would be equal to negative 8. Now that's just an example I made up off the cuff, as they say. Let's take a look at a specific example in your handouts now. Identify the degree, the leading coefficient, and the constant term of this first polynomial function. So I would like you to take in what I've just taught you, or hopefully taught you, and write in what the degree of that polynomial is, what the leading coefficient is, and what the constant term is. So the degree is 3, the leading coefficient is negative 25, and the constant term is 2. Those of you that are in calculus right now, you notice that there are many cases where we don't have the highest degree term written first, because it's more convenient to do it elsewhere, or to write it in another way. But in this course, I suppose what we should do is recognize that you would have the x to the 3 first. So the leading coefficient is negative 25, the highest degree is 3, which means the degree of the polynomial is 3, and the constant term is 2. Is that okay? Any questions with that? Okay, now, when you take a look at B, this is going to lead to a very important idea that we continually come back to in this unit. I want you to notice that these three things, let me get things going here. I don't know why it does that. There we go. When you look at these three things, I want you to notice that they are always determined by the first term and the last term. When you write out a polynomial in decreasing exponent or decreasing degree, it's the first term that's going to tell you the leading coefficient and the degree, and it's the last term that's going to tell you the constant term. Well, that statement that I just said, it's the last term that will tell you the constant term, we'll come back to that. That's not always true. What this means is if I FOIL this out, all that is important to get the highest degree term is to multiply the highest degree term in each of the factors. And this is going to become very, very important because we're not just going to have quadratics. We're going to have 5 or 6 factors later. But so these are 2 factors. This is factor 1. This is factor 2. When I take 3x times times 5x, and get 15x squared, just think about this for a second. I've multiplied the highest degree term in one factor by the highest degree term in the other. That has to give me the highest degree term in the product, which means the degree is 2, the leading coefficient is 15. If I multiply the constant term in each, then it makes sense that the only way I can get a constant term in the product is to multiply the constant term of all the factors together, which means that the constant term is negative 4. Does that make sense? Does anybody have any questions with that? In other words, and you don't need to write this down, we're going to see lots of examples like this. If I gave you the following polynomial function, then you should know that if you expand this out, you are going to get 6x to the 4. I want everybody to think about where I'm getting 6x to the 4 from. I'm multiplying all of these highest degree terms and all of the factors. You're going to get stuff, and then you're going to have minus 270. So a couple of questions. How many of you see where I'm getting that number from And can you multiply to see if I did it correctly? So the negative 270 is the product of all of the constant terms. That's the product of 3 and 2 and negative 5 and 9. And where I'm going with this is that this term and this term, these are important in terms of graphing a polynomial function in a general sense. The middle of the sandwich, all that other stuff, doesn't really tell you much about the graph. It's the first term and the last term. Let's take a look at the last example here in this section. What is the degree, the leading coefficient, and the constant term? We need to recognize that this is f of x equals 3 times 4x minus 1 times 4x minus 1 times 5x squared minus 2x plus 3. And goodness, we're not going to multiply that out. That's mathematical. That's asking for failure here, because you're bound to make a mistake. The first term, this is a little tricky. The first term is found by multiplying the highest degree term in all of the factors, and 3 is the highest degree term in that first factor. Remember, factors are things in brackets that are being multiplied. So I need to multiply 3 times 4x times 4x times 5x squared. I want to say 240. But am I right? 240. And it will be 240 x to the 4. Then you're going to have all this stuff in here, and then you're going to have a constant term. The constant term is found by multiplying the constant term in all of the factors. So this is a constant term, this is a constant term, this is a constant term, and the 3 is a constant term. So because there's a factor of 3, 3 is both the highest degree term in that factor, and 3 is also the constant term. So I multiply 3 by negative 1 by negative 1 by 3 and get 9. So now we know the degree is 240. No, it isn't. The degree is 4. The leading coefficient is 240. And the constant term is 9. Are you with me on that? Ian?
You said that for just the 3, that's one separate entity that you're multiplying.
Yep.
It has the highest degree in its term. But that.
Factor is the word you're looking for there. 3 is the highest degree term in that factor.
The only way it can be 3 is x equals x to the exponent 0.
Correct?
But 0 is the lowest you can go for a whole number in your exponents.
Yeah.
So how is 0 the highest?
Because there's only one term in this factor.
Oh, right.
There's one term. That's the term. If I said to you, which of the following terms in here, the first thing you should do is go, what's he talking about? Which term? There's only one term. So since there's only one term, that term, and the degree of that term is 0, since the degree of that term is 0, that makes it the constant term, because the constant term is degree 0. But since the degree of that term is 0, and it's the only term, then the highest degree term is 0 as well. All right, so look at this polynomial function. Q of x, why q? Why not? It's just a letter. Q of x equals 4. Why is this called a constant polynomial function? Why do you think it's called a constant polynomial function? Arden, you want to give it a crack?
Because x is always 4. And
Because y is always 4. because y is always 4. If you write this out as y equals 4, so just saying, going back to grade 10, f of x is another way of saying y, so q of x is y. And I asked you to make a table of values here so that we could plot the graph. And you said, well, -2, -1, 0, 1, 2. And you put these values of x into the function wherever there's an x. There is no x, so you're going to get 4 every time. In other words, the graph of this polynomial function is a horizontal line that's always constant. The y value is always constant. So a number of ways we can answer this. This is a constant. You could say not dependent on x. And the degree of the polynomial function is 0. So, you don't really study degree 0 polynomial functions. You don't really study constant polynomial functions in any particular grade. They're really weird functions that as soon as you get to them, they're kind of confusing. You talk about them in grade 8 and 9 a little bit when you have graphs. We talk about them a little bit in grade 10 as well because they have a slope of 0. But what we do talk about a lot, so on the next page there's a table. We don't really talk about these polynomial functions. And notice I'm just putting equals c. This is where I drop the n and n minus 1 and n minus 2 notation for subscripts. You learn about linear functions. And I would like everybody to think carefully about what I have just written here. About that. P of x equals ax plus b. What letters did we use last year for a and b? Not last year. Grade 10 for a and b. Instead of a and b, we used different letters. What were they? mx plus b, right? But, you know, I don't care whether you call the coefficient of x m, the coefficient of x a. I don't care if you call the coefficient of x a sub n. It's a letter, it's a coefficient. That's why, and I do want to go back and show you this, that's why I'm not in a real big tizzy about all of these weird subscripts, because in the end we probably don't use them. You just put a letter for the coefficient. So you've learned about linear functions in grade 10. Almost exclusively, the mathematics you do in grade 10 is about linear equations and functions. Last year in grade 11, you learn about quadratic functions. And this should be very familiar to you, right? ax squared plus bx plus c. Well, this year we're going to be learning about higher degree polynomial functions. A degree 3 polynomial function, which would be ax cubed plus bx squared plus cx plus d. And that polynomial function is called cubic. And you should recognize the word cubic as meaning degree 3. A quartic polynomial function would be degree 4. And rather than writing a sub n minus 1, all that garbage, we can just write ax to the 4 plus bx cubed plus cx squared plus dx plus e. And degree 5 is called quintic. And I don't know that you would ever see the word quintic, but you might. You would never see the corresponding word for higher degree polynomial functions. In fact, I don't even know what a degree 6 would be called. Intuitively, I want to say hexic, but I don't know that that's right. So we need to familiarize ourselves with these terms. So what's going to happen now is your teacher, that's me, I'm going to graph a whole bunch of polynomial functions so that you can come up with a generalization about constant polynomial functions, linear polynomial functions, quadratic, cubic, quartic, and quintic. Okay? And I'm not going to write all this down. I'm going to verbally explain what you should be writing down in all of those boxes. And the very first one I want to show you is f of x equals 10, which is a constant polynomial function. Now, I'm going to be developing a rule that we can use for any polynomial function. But unfortunately, constant polynomial functions wreck the rule. The rule doesn't always work for them. Okay? But I will tell you right now that what is important about this polynomial function is it crosses the x-axis in 0 places. It doesn't cross the x-axis. Could a constant polynomial function cross the x-axis? Cross the x-axis. In other words, could a constant polynomial function have an x-intercept? What if it were f of x equals 0? Which would mean it would be on the x-axis. Then it would have an infinite number of x-intercepts. That's the exception to the rule. That's what screws up the rule for everything we're going to talk about. So without talking about that exception, the key idea here is a constant polynomial function has 0 x-intercepts. And that's interesting because the degree of this polynomial function is 0. Think about that. The degree is 0 and it has no x-intercepts. What if I take a linear polynomial function, like f of x is equal to 4x minus 9? Well, this is basic grade 10 math. The slope is 4. The y-intercept is negative 9. That's what it looks like. What's important here is it crosses the x-axis in one location. And it's interesting, it's not a coincidence, that the degree of this polynomial function is 1. So the degree of the polynomial function, for a linear polynomial function, the degree is 1, and there's one x-intercept. I hope you're starting to pick up on a pattern here. Because if I go to a quadratic polynomial function, which is degree 2, there are 2 x-intercepts. But it's more complicated than saying the number of x-intercepts matches the degree. If I go back to the linear, does a linear polynomial function have to cross the x-axis somewhere? Sure. The only way it couldn't is if it was a slope of 0, but if it's a slope of 0, it's not linear, it's constant. So this linear function of degree 1 must cross the x-axis in one place. Let's go back to my quadratic function. My quadratic function has degree 2, and we're looking at a graph that has 2 x-intercepts. Does a quadratic function have to cross the x-axis twice? In other words, does it have to have 2 x-intercepts? Well, no. It could have 1 x-intercept, couldn't it? If the vertex of the quadratic function lies on the x-axis, then it has 1 x-intercept. In other words, if I take this quadratic function and I translate it up a particular distance, there's got to be a number that I can translate it up to get 1 x-intercept. And if I translate it up further, it's possible to have no x-intercepts. This has to do with quadratic functions and equations from last year and the discriminant. You can have, for a quadratic equation, 1 solution, no solutions, or 2 solutions. So for the corresponding graphs, you can have 1 intercept, no intercepts, or 2 intercepts. Can somebody tell me fundamentally, so a degree 2 can have 0, 1, or 2 x-intercepts. Can somebody tell me fundamentally why that doesn't happen with a degree 1? Why can we not have no x-intercepts, but with a degree 2 we can? This is a difficult question to answer. Why must a linear function cross the x-axis, but a quadratic function doesn't have to cross the x-axis? Arden?
Kind of maybe with like the quadrants, linear can exist in all at once.
Let me rephrase the question. I think I know what you're saying, but in terms of the shape of the graph, why can this shape end up not touching the x-axis? Marcel? Because it has a vertex, it has a lowest point, right? In this case, or it could have a maximum point. And it's interesting to note that the only way you can get a vertex is if both ends are going up or both ends are going down. And this is the difference between this polynomial function that you're looking at. We call those ends arms, where both arms are going in the same direction. Whereas with this polynomial function, and if you're watching this on video, you're missing my arm gestures, but with this polynomial functions, the two arms are pointing in opposite directions. So if you go from negative infinity on the left, which is what I'm pointing at with this finger, to positive infinity on the right, I don't care what happens in between, you've got to cross the x-axis. Okay. What if we go to a degree 3? Well, it probably shouldn't be a big surprise that if a degree 1 has one x-intercept and a degree 2 can have two x-intercepts, then a degree 3 can have three x-intercepts. So do you believe it's possible for me to draw this general shape, but it's not going to cross 3 times on the x-axis? It's only going to cross twice. The word cross is deceptive. Maybe cross is the wrong way to put it. Can I draw this general shape so that there are only 2 x-intercepts? Well, if I shift it up, but I don't shift it up too much, I shift it up that much, then there are 2 x-intercepts. So a degree 3 polynomial function can have 3 x-intercepts, or it could have 2. Is it possible to have 1? Well, if I continue to shift this up, certainly we can have 1. Is it possible to have 0? No, it's not possible to have 0. And the reason is that the 2 arms are going in opposite directions. Now, this gets a little bit tricky, but I hope you're seeing the reason why these 2 arms are going in opposite directions for a cubic and for a linear is the degree of those polynomial functions are odd. Degree 3 is an odd number. The only way you can get 3 x-intercepts is if the arms are going in opposite directions. Linear is degree 1. 1 is an odd number. The arms go in opposite directions. We're going back to the title page here soon to explain why John Travolta's stance is odd. Because it matches a cubic polynomial function, which is odd, and the arms go in opposite directions. Can you have a degree 3 polynomial function with 0 x-intercepts? No. So we come up with another rule here, and that's that if you have an odd polynomial function, there has to be at least 1 x-intercept. But there can be more than 1 all the way up to the number of the degree. So forgetting about degree 0, because that's the weird one. Degree 1 is odd. It has to have 1 x-intercept. Degree 2 is even, and it can have 2, 0, or 1. So if it's an even degree, it can have no x-intercepts because the arms are both in the same direction. Or it can have any number less than that number down to 0 if it's even. Let's see if this kind of works for, well, let's go to degree 4. Probably not a surprise that degree 4 can have 4 x-intercepts. And I'm not going to go to great lengths to explain this, but I hope you understand the only way you can draw that shape to cross the x-axis in 4 places is to have the 2 arms pointing the same way. Because if one of these arms was going down, then what that would mean is there would be a fifth x-intercept, potentially. So let's cut to the chase here and see if you get my point I made earlier, among others. Do you think that a degree 4, a quartic polynomial function, can have 0 x-intercepts? Sure. Just have to shift it up enough so that it's lying entirely above the x-axis in this case, and it could have 0. Could it have 1? Well, if I just move this thing down just a little bit. Whoops. Then it has 1. Could it have 2? Well, let's move it down a little bit more, or a lot. It doesn't matter. There's lots of ways you can do this. It could have 2. Could it have 3? Sure. And it can have 4. So because it's an even degree, degree 4, it can have 4 x-intercepts, or 3, or 2, or 1, or 0. Because it's an even degree, it can have 0. Let's go to degree 5. I think you get the idea, but there's a degree 5, and if you count the x-intercepts, you will see there are 1, 2, 3, 4, 5. Could we have 4? Sure. It still has that shape. Could it have 3? Yeah, I can move it up and down to get 3. Could it have only 2? Sure. Could it have 1? Definitely. Can it have 0? Well, no, because if the arms are going in opposite directions, it has to cross the x-axis somewhere. And again, the arms are going in opposite directions because it's an odd degree. So going back to your handout, you should already have written this. A constant polynomial function has 0 x-intercepts, and there's that little exception that if it's on the x-axis, it's infinite. A linear polynomial function must have 1 x-intercept. A quadratic can have 2 x-intercepts, but it could have 1 instead, or it can have 0. Cubic can have 3 or 2 or 1, but it cannot have 0. Quartic can have 4 or 3 or 2 or 1 or 0 because it's even. Quintic, that's an odd degree. It can have 1, 2, 3, 4, or 5, but not 0 because it's odd. All right. So what does this tell us? It tells us that an odd degree polynomial function has arms that go in opposite directions. And I don't care what it does in between here. That's not the point of this picture that you're looking at or that I've drawn. How many times it wobbles up and down, it's a complicated issue. It depends on degree, and it also depends on some other things which we don't need to worry about right now. There's stuff going on in here. There's a haze of stuff happening in here that's unimportant. The odd degree could also look like this, right? And again, something's happening in here that we're not really caring about right now. An even degree must have arms that go in the same direction. And there's something else happening, but it's unimportant to this point. An even degree could also have that. Now, how can you tell whether, looking up here, I'm just going to label these. How can you tell whether it's A or B? How can you tell whether the graph will look like this or like this? If it's C or D, well, you can tell it's A or B by finding out whether it's odd. If it's odd, it's A or B. If it's even, it's C or D. But how can you distinguish between whether the arms are in one particular orientation or the other? Well, I'm going to go to my graph again. And I am going to put up all of these. It's going to get really ugly, with the exception of the constant degree or the constant polynomial function. Whew. Wow. There are all of the polynomial functions. And it's a mess, right? What do they all have in common? What do all of those graphs have in common? If you see it, put up your hand, but then you can put your hand back down because I want everybody to think about this. They all share something in common. You got it? On the right-hand side, they're all pointing up. When you look at all of the arrows over here, up, 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 up. These are all going up. When you look at the left-hand side, some of them are going up, some of them are pointing to the sky, some of them are pointing down. And if you were to look at all of the equations of the functions I've entered, I'm going to turn these off now and just show you some of them. I'm going to show you the following. What do all of these equations have in common? And the answer is the leading coefficient is positive. Now, I'm showing you those because if I show you some of the other ones, like this one, I've just got a different label there, but I can open it up and show you that it says positive x to the 4. So the right-hand arm goes up if the leading coefficient is positive. Everything else is unimportant in terms of my diagram and my point being made right here. Because if it has a positive leading coefficient, the right arm is up. The only thing you could say about the left arm, unless you look at the polynomial function, is I don't know. But if the polynomial function is odd, then the left arm must go down in the opposite direction to the right arm. If you have a negative leading coefficient, well, let me show this to you. These are all negative leading coefficients. Negative 0.5 x to the 5. Negative 0.5 x to the 4. Negative x cubed. Negative 2x squared. Negative 5x plus 7. When you take a look at all of the right arms, the arm on your right, they are all pointing down. And again, everything else about the graph you cannot determine unless you look at other features of the graph. Like, is it odd or the function? Is it odd or is it even? Any questions on that? All right, we have one more thing that we want to take care of, and it's what the positive constant term and the negative constant term tell you. Well, let's go back to one of these. And I'm not even sure we need to talk about positive and negative. Let's talk about the constant term. If I take a look at y equals 4x minus 9, the constant term is negative 9, yes? Is there something about the graph that's connected to that negative 9? Jonathan?
Well, the function hits the functions on the y-axis.
Right. It's the y-intercept. The constant term of a linear polynomial function is the y-intercept. What about a quadratic polynomial function? This is 15x squared plus 4x minus 5. Crosses the y-axis at negative 5. This should make sense to you, everybody, because the y-intercept is where x is 0. If you put x equals 0 here and here, the only thing that survives is the constant term. And if we take a look at a different one, let's take a look at this degree 5 polynomial function. You can see, looking up here, that the constant term is 0. It's x to the 5 minus 7x to the 4 plus 11x cubed plus 7x squared minus 12x. The constant term is 0. Crosses the y-axis at 0. So what we learn from that is that a positive constant term has a positive y-intercept. And a negative constant term has a negative y-intercept. In fact, I'm not quite sure why I made a big deal about positive and negative. The important point is the constant term is the y-intercept. That's what's important. So if the constant term is positive, the y-intercept is positive. This lesson started by talking about highest degree term and constant term because those are the things that tell you, are both arms up or down? Okay, well, if it's an even degree, both arms are either up or down. If it's an even degree with a positive leading coefficient, then both arms are up, because a positive leading coefficient means the right arm is up, and if it's even, both arms have to be in the same direction. So you have to look at the leading term and the constant term to determine properties of graphs. And again, I hope you catch my drift here, that these shapes are generally speaking the same. Those are not the only shapes John Travolta is capable of. So there's a degree 4. I don't know what that is. It just gets more and more embarrassing as you go on. It's a great movie. See if you can find it online. Staying Alive. No, it's not worth your time. Don't waste your time. You can see that there are some practice problems, as is the case usually. We have multiple choice and numerical response in your textbook stuff.